Alright, today's lesson is lesson number 94. We're going to be talking about the Pythagorean Theorem. The Pythagorean Theorem is something that has probably come up in 7th and 8th grade, especially 8th grade. There's a lot of standards that have to do with it in that year. The reason that we are reviewing it now, though, is because the Pythagorean Theorem really helps us out in geometry. It's something that you need to just know and be able to use very easily. So, we're going to spend some time on it today. Okay, so first of all, remember the Pythagorean Theorem states that in a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. So that's kind of in words what this equation tells you. Okay, so this says the sum, because it's addition, of the squares, okay, they're both squared, of the legs. Okay, so I'm adding the squares of the legs, and that's going to equal the square of the hypotenuse, C. Okay, remember in a right triangle, the hypotenuse is going to be the side across from the right angle. Okay, sometimes we learn that it's the diagonal side. I really don't want you to look at it that way, because we can always have a triangle that looks like this, okay, where, let me do this, something like this, where this is the right angle, so the hypotenuse is down here, okay. We can have triangles turned and rotated all sorts of ways. It doesn't make it not a right triangle because of the way that it's turned, okay. So think of the hypotenuse as the side across from the right angle. Okay, that means it's the longest side in the triangle. So we call this the hypotenuse, and then the other two sides we call the legs. Alright, so if you were absent, make sure you write down both of these definitions, okay? So the definition in words and then the equation version, okay? We also watched this video in class, so I'm going to pause and I'll switch over to show some things that focus on that. Okay, so this part here is showing you that this square is C squared, okay? The long side in the yellow triangle, okay, across from the right angle would be C. Let's write over this. So this would be like my A and my B. This is the right angle. Then this side across from the right angle would be C. So that means that this side is C, right? You saw it swing out to map the same length. These are congruent. So this side is also C. So the area of this square would be C squared. Okay? Okay, so they're showing you that those triangles are all equal. They can make this bigger square by turning it. Now if we move the triangles this way, we end up with two different squares. And let's look at this a little closer. So we saw they just copied the same square over here, right? We have 1, 2, 3, 4 of these yellow triangles. This first triangle stays where it is. The second one kind of swung down, right? So it's over here now. The third one moved over, and it's here. And then the fourth one swung down and went on top of the third triangle. So the fourth triangle went here. Okay, so since the big squares are the same size, they must be the same area. And they have the same number of triangles that are all the same area. So, okay, that's telling me this red square must equal the areas in the blue and the green. Right? These must add up to C squared. And if we look at our original triangle, the side lengths here, okay, remember the short side I labeled earlier as A, the longer leg I labeled B, and then the hypotenuse is C. Okay, so these are all the same triangle though, they're all congruent. So this long side here is B, this short side's A. In triangle 2, this is A, this is B, okay, and so on. So we can see that this blue square right here is actually a squared, and the green square is b squared. Okay, again, we said, well, these two things are the same size, so the area overall must be equal. The triangles kind of cancel out, right? There's 4 in each one. So what I'm left with is a squared plus b squared must equal c squared. Okay, again, those areas must be equal, and what you're going to see now is that no matter which, it's going to look like this square is rotating, but what it's showing you is that the side lengths of the triangle don't matter. Okay, the Pythagorean theorem is always going to hold true. Okay, so let's see that here. See, no matter what happens, we still have this a squared plus b squared equaling c squared. And you can see that in this final diagram, right? It puts it all together. This is the one triangle that we were talking about. So the short side a, that square, the blue square that represents a squared, plus the green square that represents b squared must equal the red square, which is c squared. Okay, so just a little video to show us kind of a visual proof. Okay, so hopefully this helps you to kind of buy into the idea of the Pythagorean theorem. Okay. All right, so back to the lesson. Here are the steps. If you were not in class today, go ahead and pause here, write these down. Basically, you're just going to label the side lengths appropriately, depending on if they're a leg or if it's the hypotenuse, and then you'll plug the values into the Pythagorean theorem and solve for what's missing. Okay, so here's some examples on number 1. They're both right triangles, but here's the right angle for number 1. Okay, I'm trying to find this side. I know it's the side across from the right angle. Okay, so that must be my hypotenuse, which is c. So I have my Pythagorean theorem, a squared plus b squared equals c squared. I'll plug in 4 for A and 3 for B, since those are the lengths of the legs. Okay, here and here, right? And now I'm going to solve. So 4 squared is 16, 3 squared is 9. 16 plus 9 gives me 25, so I have 25 equals c squared. Okay, but I don't want to know c squared, I want to know c, so I have to take the square root of both sides, and I get c equals 5. Okay, over on number 2, this is my right angle here. I see that 5 and 13 are two sides that are given to me, and I want to use the Pythagorean theorem. 13 is my hypotenuse, or c, because it's across from the right angle, and then 5 is the length of one of the legs. Okay, so I'll call that A, and then the other side is B. Plugging in 5 for A, I get 5 squared plus B squared equals 13 squared. 5 squared is 25, and 13 squared is 169, so now I have this as my equation. I subtract 25 from each side. I get B squared equals 144. And then I take the square root of both sides and get B equals 12. Okay, a couple things to note here. First of all, you'll notice that both of these gave me whole number answers, and that is not always the case. Okay, sometimes we're going to just have a radical that we have to simplify. So maybe instead of square root of 25, I end up with square root of 32, right? So that's not a perfect square, but I can simplify it. The other thing to notice is that back when we were taking the square root of both sides to solve just equations, we would write c equals plus or minus 5 as our final answer after this point. Okay, but for triangles, we're just going to focus on the positive case because we're talking about side length. Okay, so just a little bit of background that we should know. Also, like I mentioned, these are not always going to be whole numbers. When it does work out that we have whole numbers, we call that a Pythagorean triple. Okay, so when the side lengths of a right triangle are all whole numbers, we call that a Pythagorean triple. Alright, so both of these would be examples of those. Okay, 3, 4, 5, and 5, 12, 13. Alright, moving on to our next example. Number 3 I didn't do in class. I can do it right now. Okay, so I use the Pythagorean theorem again. I see this is the right angle, so 10 would be my hypotenuse, which is C. 6 is going to be either A or B. I'll call it A, just why not? So I plug in 6 for A and 10 for C. That gives me 6 squared plus B squared equals 10 squared. 6 squared is 36, 10 squared is 100, and obviously B squared I can't really simplify. So now I want to solve for B. I do that by isolating it. So first thing I need to do is subtract 36 from both sides. Okay, when I do that, I get B squared equals 64. Taking the square root of both sides, I get B equals 8 as my final answer. Alright, and looking at number 4. Okay, again, this is the right angle using the Pythagorean Theorem. 17 is C because it's across from the right angle. Okay, it's across here. 8 is a length of one of the legs, so I could call it A or B. Maybe I'll call it B this time just to switch things up a little bit. So I have A squared plus 8 squared equals 17 squared. 8 squared is 64. 17 squared is 289. Now I want to isolate the A, so first thing I need to do is subtract 64 from both sides. Okay, when I do that I get A squared equals 225, and taking the square root of both sides I get 15. Okay, so again these are two more examples of Pythagorean triples. 6, 8, 10 is really just like 3, 4, 5. Okay, it's all of those numbers multiplied by 2. But it is another example. And then over here we have 8, 15, 17. So that's another example. And that's different from the 3, 4, 5, right? It's not a multiple. Okay, so moving on to our last two examples. Number 5. Okay, this one, it looks, a lot of kids were like, oh, it's upside down, or it's tilted. But a triangle is a triangle. Okay, there's no correct orientation for a triangle. They certainly can look like this, so we just have to be aware that this is the right angle, which makes the side across from it the hypotenuse. Okay, so this is going back to the definition that some kids first learn of the hypotenuse being the diagonal side. And that's not really the case here, right? I see both of these as diagonal sides, but that's neither one of those is the hypotenuse. Okay, this is the hypotenuse where I have it labeled as C because it's the side across from the right angle. Okay, so we're solving for C here. I use my Pythagorean theorem once again. If I plug in, I need to plug in 4 and 8 for the legs, A and B. It doesn't really matter which order I plug them in. So I did 4 for A, and then 8 for B. So I got 4 squared is 16, 8 squared is 64. So 16 plus 64 equals C squared, which gives me 80 equals C squared. Okay, I take the square root of both sides, and now I have C equals the square root of 80. This is not a perfect square, so I need to simplify the radical as much as I can, which is going back to yesterday's lesson. Okay, so in 80, the biggest perfect square is 16. So if I divide by 5, I get 16. So I'll do 80 equals the square root of 16 times 5. 16 is just 4 squared. So the 4 comes out of the square root, and that's my final answer. Okay, so this is an example where we don't get a whole number. Okay, there's still a radical involved, and that's completely fine. Okay, and in this last example, number 6, where it's labeled C, that's the hypotenuse because it's across from the right angle. The 5s are both legs, so in my Pythagorean theorem, I would have 5 squared plus 5 squared equals C squared, which just gives me 25 plus 25 equals C squared, so 50 equals C squared. I take the square root. I get 60 equals the square root of 50, which is not a perfect square, so I rewrite it as the square root of 25 times 2. Okay, I know that 25 is a perfect square. It is 5 squared, so I'll rewrite it that way, and the 5 gets to come out. So 5 rad 2 is my final answer for the hypotenuse here. Alright, so that is what we did today. Please practice this on the homework problems. You'll notice there's also problems that give you lengths. So it'll say, what if I had the lengths 5, 5, and 6? is that a right triangle? And you would test that by saying, okay, what's 5 squared plus 5 squared? Is that equal to what 6 squared is? Okay, so you test a squared plus b squared, then c squared, and see if the two sides are equal. If they are, then yes, it's a right triangle. If they are not, then no, it's not a right triangle. Okay, so that's it for today. Good luck on the homework with this, and I will see you tomorrow.